that what we had was all of our protons. So all of our protons sit in this super dense nucleus. Our electrons then float around somewhere on the outside of it. Where? Didn't really know, but the experiment didn't test for that. It was really just looking for that nucleus. One of the kind of concepts that can come out of this is we lose kind of an understanding of the relative size of an atom to a nucleus. So we mentioned size. What does size mean to you? How big? Right. So if we looked at a pound of feathers versus a pound of lead, which one's size is bigger? Okay. So cool, I actually like it that you guys said feathers. We're looking at the volume that it's occupying. When we think size, it's volume. It's not mass. So when we look at our Rutherford model for our atom, our protons are jammed into a very, very tiny space. So when we move from one element to the next, we may be adding protons, but that has very little effect on the size of the atom, because the protons are all jammed into the nucleus, which is now an incredibly tiny place. That tiny space now has a massive volume, but it doesn't contribute to the size. The size is due to, we just said it's not the nucleus, which means it can't be the protons. What's the only other particle we have at this point? Electrons. Our electrons are contributing the size of our overall atom. So if we compare the size of our atom to the nucleus to get an idea of scale, if we take the nucleus and scale it up to the size of a marble, okay, relatively tiny, the size of your average atom is the size of the superdome. Okay? So a single marble is our nucleus. The superdome, massive stadiums, okay, are the size of the atom itself. Okay? So we're looking at a very huge distinction in size. We're jamming all of those protons in a tiny, tiny, tiny space. Okay? It's an important distinction to make, particularly if to move into organic chemistry, because one of the things we're concerned about is then how do molecules interact with each other? Okay, well, what's the most likely thing our atoms are going to see when they interact with each other? The electrons, because they're on the outermost part of it. Very rare for our protons to ever interact between atoms. It's the electrons that largely do that interaction. Okay. So after Rutherford, kind of, we'll keep seeing scientist names pop up, but he's kind of the last big scientist name to remember. So he had predicted that we have to have a neutral particle. What's the evidence for that neutral particle? So we could look at mass, and we'll come back to you in just a second. We could look at the mass. Notice that if we just had protons, it doesn't add up right. There's something a little bit off with our mass. So there has to be something else there contributing to the mass. What was your suggestion? Well, the alpha particles come in and they encounter a massive nucleus, which could still be protons. Okay, we know that that nucleus is positive because our alpha particles bounce. Okay, so that still tells us that we have a positive nucleus, not that we're missing a neutral species.
Could it be because of the charges?
What happens if you bring like charges near each other?
They repel.
They repel. So if I take two protons, which are positively charged, and I now put them in an infinitely tiny space, what happens? Expect them to push away from each other. Okay? So Rutherford comes to this conclusion that they must be located in this infinitely tiny space. Okay? But there would naturally be a repulsive force. So why are they being held together? There has to be something else there holding those particles together. That particle he theorized to be a neutron. Okay? Direct evidence of that didn't come about until James Chadwick, some years later, I don't remember the exact year, I think 1920s maybe, was actually able to find and discover a neutron. Okay? And with that neutron discovery, he ends up determining that it's neutral in charge, but it has the same mass as a proton. So at the end of all of this, we end up with this nice, fun conclusion, table 4.1, that gives us all this information about them. We have our three subatomic particles, electron, proton, and neutron. Those words are too hard to write out, so we come up with a symbol. Symbol for an electron E. Back to Sesame Street. We picked E because electron begins with E. Okay, relatively straightforward naming system when it comes up with those. You'll also notice that you see this minus, this plus, and a 0 next to each of those symbols. And those charges, let's say charge, negative, minus, the negative, the positive, and that 0 say something about the charge of that particle. An important thing to note is, where is that written? Not just after. It's also written as an exponent. The upper right-hand corner for all chemistry tells you information about the charge of whatever you're looking at. So by writing that negative sign in the upper right-hand corner of the E, we're now saying that I am looking at an electron with a -1 charge. You'll notice that we're referencing as relative charge. These are not absolute charges. We can go back to Millikan and look at what the absolute charge was on an electron. We don't want to memorize that number. Okay? But what we do realize is that the relative charge is the same. Okay? Or the absolute value of our relative charge is the same. This is where we can deal with the -1, the +1, and then ultimately for our neutron, 0. Why 0 for the neutron? It's neutral. It has no charge. Okay, so you are responsible for recognizing those charges. If we look at the symbols already tell you the charge, so you may not have to memorize that. The next part of it comes down to the relative mass. Protons and neutrons are characteristic or subatomic particles that contribute mass. We define that mass to be 1. Okay, 1 what? We could say 1 subatomic particle, but then if I go up to electrons, isn't an electron a subatomic particle? Why is that not 1? What is the unit on that 1? And it's kind of related to our subatomic particles. We go through and we define our proton to be a mass of 1. Okay? And we will call it AMU, which is a fancy way of saying atomic mass unit, which in English means I made up a unit so that the mass is 1. That's all it is. Okay. Interestingly enough, we will come back to this meaning of what an AMU is, and it will relate and mathematically work out such that we can derive the concept of a mole. Okay? And we still end up with roughly 1 for our mass unit. Okay? The important aspect here to remember is that those contribute 1 mass unit. If I know the mass unit of a proton to be 1, I know the neutron has the exact same mass. So if the proton is defined as 1, what is the neutron? 1. Relatively straightforward. What about the mass of an electron? It is still matter, so it does still have a mass. That mass happens to be 1 over 1,836, the mass of a proton, which means it's roughly 0. Okay. Electrons do carry a mass, but for all purposes that we would go through and use, at least at this stage, the mass of an electron is roughly the same as nothing. Okay? So if I wanted to figure out the mass of any element, what do I need to do? Figure out how many protons and neutrons. That's it. Total those up, I now have the mass of my element. In what units? AMUs. Okay? So a relatively straightforward system. Questions on that? Okay.
Would it be just impossible to find the actual mass?
No, we can actually determine the actual mass in grams or kilograms, and it's, well, I'm making numbers up, but I think it's 9.116 times 10 to the minus 17 grams. So really, 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 really small. Okay. So which number do you want to memorize? The one that I just made up, or 1? 1 makes sense. Okay. If you have to move in through more chemistry, you say you want to become a physicist, nuclear physicist, then the mass becomes a little bit more important and you'll want to know it in grams. Okay. At this stage, we don't need to know it. But since you asked, we'll do a conversion to figure out what it is later in the semester. Next thing we come across is atomic notation. Okay. It is often referred to as nuclear notation. Okay, and we'll discuss why in just a second. We have a characteristic number of protons and neutrons and a symbol that we could associate with any given element. So what we're trying to do is now specify that all in one simple condensed format. So our condensed format is whatever our element is, we provide its symbol. Okay, so in this case, symbol, SY for, symbol. Fine, thank you. The next part is specifying our protons and neutrons in some fashion or another. Okay? The protons we'll define as the atomic number. The protons will get written in the lower left-hand corner of our symbol, where they belong. How would I specify the neutrons? Well, I could just arbitrarily place the neutrons wherever I want, but then I don't come up with quite as useful a value for it. So instead what we do is report the mass for that symbol, okay? And in particular, the mass number. The mass number is now going to be the sum of the protons and neutrons. And that I will write in the upper left-hand corner of my notation. Where in this notation do we specify anything about electrons? Nowhere. Interesting. Why would I refer to this as the atomic notation? It doesn't make sense to refer to it as atomic notation because an atom has electrons, and nowhere in this have I specified the number of electrons. Okay. Remember how we specified on those earlier slides where we could say some information about the charge of each of our particles, the electrons, the protons, the neutrons, what their charge was? Where was that? Where did we specify the charge on an electron? I wanted to write an electron. What's the symbol for electron? E minus. What did that minus mean? That particle was negatively charged. Nice. Okay. Does our notation down here also include that information? Yes, it does. What does it show in the upper right-hand corner? Nothing. What is the charge on this element as written? Nothing. How do we determine the charge then? Or sorry, the electrons. So in that upper right-hand corner, we now have the charge specified for us. Because it's 0, we don't have to write it. If it's any other number, we have to specify it. Okay, so in this case, we have an implied 0 telling us the charge on this element is 0. Where would I provide, or how would that tell me information about my other subatomic particle? What's the other subatomic particle missing? We have protons, we have neutrons, we are missing electrons. Somehow or another, that charge needs to give me information about the electrons. How?
They're equal to the protons.
How do you know they're equal to the protons? We have 0 overall charge, which means the number of protons plus the number of electrons must equal my overall charge. In this case, if it's 0, the number of electrons must be the number of protons. So now we can reference it as our atomic notation by adding this extra little bit of information and realizing that our charge is specified within the notation. Most often when we're looking at this notation, we tend to ignore the charge because what we're looking at is what's happening with our nucleus, which is why it's sometimes referred to as nuclear notation, because we're looking at our protons and neutrons. Okay? So this notation now gives us the ability to identify how many protons are present, how many neutrons are present, and how many electrons are present. We now know all of our subatomic particles for an individual element. Okay. Where could we find this information on a test? So number one, more than likely, you weren't given any of that. So where do you find that information on a test? The periodic table. Right? So if we go back to that symbol, we said the mass number was located where in our atomic notation? The upper left-hand corner. Where is the mass number on our periodic table? On the bottom left-hand corner. Well, that's pretty awesome. Why did they move it to a different location?
Because it looks cooler.
Right. Good question. Who knows why they moved it and put it in a different location? Or do you actually have a good idea? I don't.
To get at the neutrons, so you, I don't know, never mind. I was gonna say, because to figure out the neutrons, because you do and the mass
Well.
number with the atomic number.
But why on the periodic table are we putting the mass number in a different location?
I don't know, but I was saying that for that one, the reason why is so as you look at negative number, and you're minusing to the top to the bottom.
So here we could do a standard formation to find our number of our neutrons by doing what? I understand what you're trying to do now. A minus Z gets you the number of neutrons. It's formatted in a nice, strictly quick and easy calculation. So that makes sense for this notation. Why does it not make sense on the periodic table? Who knows? Okay. One possibility is that when we look at the periodic table, does it give you the mass number? So when we look at the periodic table, where does it say the mass number? So several people said the bottom of an individual element. Why did you say the bottom? Atomic weight is what it's on the periodic table, not the mass number. What if they'd said the atomic mass? Also, not the mass number. That's all sorts of weird and confusing. What is going on with that? The mass number refers to a specific atom. Okay? And if we have a group of atoms, and then we could say it refers to that group of atoms. But the periodic table does not refer to a single mass number of an element. It refers to many different mass numbers of that element. Wait, what does that mean? How could I have, say, carbon with a mass number, let's pick something a little bit further off. Let's look at chlorine, Cl, number 17. Atomic weight of 35.45. To determine our mass number, it's the sum of our protons and neutrons. How do I get a 0.45 from the periodic table? The electrons had how much mass? 1 divided by 1,872. So to get even a half value on there, how many electrons do I need? 900 electrons. Chlorine didn't have 900 electrons. So it's not a bad idea. Maybe that's due to our electrons. It's not due to our electrons. What happens if I change the number of neutrons? What is the charge on a neutron? Nothing. So if I change the number of neutrons, does it change the charge? No. Does it change the element?
No.
What element would I be if I had chlorine with 38 neutrons? I would still be chlorine. I'm just a heavier, fatter chlorine. Okay. Its weight is different. When we change the number of neutrons, we don't change the element. What we change is its weight or its mass. So when we look up a mass number, that by definition is the sum of protons and neutrons. If I look up the atomic mass, now we're looking at an average of all the possible different neutrons that could be associated with that element. which may seem a bit weird, and we'll look at that extra terminology in a few slides. Okay. So our mass number is technically not on the periodic table. A rough equivalent is. The rough equivalent is the atomic weight, but it is not one and the same thing. What about the atomic number? Where's the atomic number on our periodic table? Upper right. Okay, so again, they're placing it in a different location. Well, maybe they mean something else. What's in the upper right? According to the legend, it's atomic number, which is atomic number. Why they put it in a different location? I don't know. Confuse you? I got no clue on that. Okay. But this is our standard notation. So given a notation, you should be able to predict the number of protons, the number of neutrons, the number of electrons. Okay? Given the element off the periodic table, you should be able to tell me the number of protons, the number of electrons, assuming you know its charge, and you can guess at the number of neutrons. Why can you only guess? The periodic table doesn't give you the mass number. It gives you the atomic weight, okay, or even the atomic mass. Okay? It's not giving you the exact amount of neutrons. Okay, so let's take a look at an example. So if I'm giving you this notation, 29 silicon 14. The element is, well, that was dumb. The element is silicon. How do we know it's silicon? Give me a little bit more than I told you. I know, I did, but that's... You're supposed to know that Si is silicon.
I was going to go with the atomic numbers 14.
So if we go with the atomic number being 14, how do you know it's silicon?
Because of the periodic table.
14 matches what?
I have no idea.
Si, which is
Yeah.
the exact same thing that's already shown. So you'd still need to know that silicon is Si. What is our atomic number? What is the mass number? 29. Why is it not 28.09?
Because it's giving us the examples.
In the notation given to you, that's where you find the mass number. Not the periodic table. You have to find it from the notation. Okay. How many protons are in this structure? And we know that because it's equal to our atomic number. How many neutrons do we have?
15.
We would take our mass number, 29, minus our atomic number, 14, and we get 32. At least somebody looked at me weird. It's 15. Okay, so we end up with 15 neutrons. Like, can I trust this guy to tell me what's going on?
He's my teacher after all.
Yeah. That'll teach you. Okay. Another way that you could go through and format this is instead of writing it out as the atomic notation, you may also see it referenced as silicon with a dash followed by which number? It'll be followed by the mass number. Why would we not follow that with the 14? If it's silicon, we go to Si. What is the atomic number? It's 14. It's straight off the periodic table. So saying silicon 14 doesn't give us any information about the number of protons. What we're trying to do is figure out its mass. So we're referencing silicon 29. That is the mass number for that particular atom of silicon. Hi. How many electrons?
14.
How do you know it's 14?
Protons and electrons are the same amount.
If we look in the upper right-hand corner of our atomic notation, what do we see?
No charge.
Nothing, which means 0 as our charge. The number of protons must equal the number of electrons. If I got 14 protons, I've got 14 electrons. Okay? Questions about that? Okay. All this is the... Let's skip to that guy. So, I only recently really actually discovered the difference between our atomic number and our mass number. So on our periodic table, we can only use the periodic table to obtain the atomic number. We cannot get the mass number. What we can get would be the atomic mass. Two different things. Okay? So what do we mean by that? If we go through and take a look at carbon, we're going to come up with its notation. Number one, we've got a C, because carbon begins with C. Close enough. What is its atomic number?
6.
Where do I write that?
To the bottom left.
The bottom left. Okay. Where do I write its mass number? Where would I write the mass number? I don't know what it is yet. Where would I write it? The top left. So my mass number should go up here. Do I know what it is? At this stage, I don't. Okay. I know the atomic mass, but the atomic mass is not the same thing as the mass number. Okay. And this is coming from looking at all of our atomic masses and noticing that most of them don't end with zeros. Some do, but most do not. Most have some weird decimal value coming off the end of that. But if our atomic mass is based off of our mass number, which is based off the numbers of protons and neutrons, why does the periodic table give us this weird decimal value? It comes back to what each of the subatomic particles contribute. Okay, so it's thinking about what they are going to do for the overall compound. So this is how I like to think about and look at our protons, neutrons, and electrons. The protons will define the element. What do I mean by that? Tells you what it is. If there are 6 protons, that atom, carbon. What if there's 7 protons? That is not carbon. Good quick answer. What's the correct? Is nitrogen. What if it had 6 electrons? Really be anything. We'd need to know some more information. We'd have to know the number of protons. Okay. The electrons just tell us our charge. Okay, or at least give us an idea of it. Okay, and you might say, well, don't you need to know the protons to know the charge? Yes, you would. But you already know the number of protons because they defined the element. Okay? So once we've started with the protons defining, we're now saying, what do these extra subatomic particles give me as more information? The electrons will define my charge. If I've got 6 protons, what's the charge? Hands up in the air may not be a bad idea. I don't know. What do you need to know? The number of electrons contributing to balance out that charge. So the electrons will define your charge. What do the neutrons define? There it was. The neutrons will define the mass. Okay. We're all humans. Do we have different mass? Yeah. So if we have carbon, can I have a carbon with a different mass from another carbon? Yeah. How? I can only change the number of neutrons. Because if I change the number of protons, is it carbon anymore? No. If I change the number of electrons? Makes the charge different, but I asked about the mass. The electron's mass is effectively 0, so it doesn't affect the mass. Once I've defined what the element is, I'm going to define my mass based off of the number of neutrons. And one of the things that we've discovered is that every element can have varying amounts of neutrons. Why did we even theorize that we needed neutrons? to keep the protons together in the nucleus. Our neutrons are acting like glue. If you need to glue two things together, there's probably an optimal amount of glue, but what happens if you use too much glue? It gets heavier. Do those two pieces still stick? Yeah. So we can vary the number of neutrons. There's a minimum amount to make sure the nucleus is now all as one piece and the protons are all stuck. But the maximum amount could theoretically go on forever. We could jam as much glue as we wanted into any given nucleus. What is that going to do to the mass of the nucleus? It increase it. It becomes heavier and heavier. There are certain combinations of glue that make sense. If you wanted to glue two pieces of paper together, how much glue would you use? Not very much. Okay. Could I use 5 pounds? Would that glue those two pieces together? Yeah. So I could use 5 pounds. Okay. Is that a bit excessive? Yeah. Okay. If I asked you guys to use glue to glue these two pieces of paper together and we checked how much glue you used, you would not all use the exact same amount of glue, but it would be close. That's the same kind of thing happening with our elements. We put these protons together, we now need to add glue. So there's an imaginary person putting glue on these, keeping those atoms together. But the amount of glue that goes into it can vary, which means the mass varies. Well, if the mass number varies, what's going to happen to the atomic mass? It's also going to vary. So the number reported on our periodic table, while being related to the mass number, is a better way of taking the average of how much glue was necessary to make that carbon atom or that carbon nucleus a carbon nucleus. It's the average of them. Okay. What we are looking at, right here, are isotopes. If we change the number of neutrons, we're now going to define the isotope. Okay. Which I thought this slide came up after or before this one, so we'll just stop with that.